Welcome to today's Visual Explainer. We are going on a zero to hero, one-shot breakdown of optics. Now, if you've ever found physics a bit intimidating, honestly, don't sweat it. I promise that by the end of this session, you are going to absolutely master the fundamentals of light and reflection. We're going to take the invisible and make it completely visible.
Okay, let's dive into this. Have you ever actually thought about how we see the things around us? Like, really thought about it? I want you to imagine pitching a pitch-black room. No windows, no lamps, literally nothing. In that absolute total darkness, even the most obvious objects right in front of your face just completely disappear. Without light, vision is totally impossible. But what exactly is light doing to make things pop into existence for us?
Well, when light hits any surface in the universe, it can really only do three things. A portion of it can be transmitted, which just means it passes straight through, kind of like sunlight through a clear glass window. A portion can be absorbed, where it essentially gets trapped as heat, and a portion can be reflected, bouncing right back. But here's the kicker. For us to actually see an object, that reflected slice is the absolute hero. If an object doesn't bounce light into our eyes, it is virtually invisible. So here is our roadmap for today's explainer. First, what is light? Second, the laws of reflection. Third, the plane mirror truth. Fourth, spherical mirrors unlocked. And finally, fifth, real-world mirror applications. Section 1. What is light? Let's unpack the basic building blocks. There are a few absolute requirements for sight. And honestly, if you remove even one of these, seeing anything becomes totally impossible. First, you need a light source emitting tiny energy packets called photons. Second, you need a reflecting object, meaning it can't be perfectly camouflaged or totally transparent. And third, you need functioning eyes, which essentially act as open camera shutters to let those photons in. Oh, and a totally crucial property to remember here, light travels in perfectly straight lines, which physicists like to call rectilinear motion. And you know, it doesn't just travel straight, it travels with absolutely mind-blowing speed. In a vacuum, light zooms at 300,000 kilometers per second. That's 3 times 10 to the power of 8 meters per second. But keep in mind, this is its absolute speed limit in a pure vacuum, like out in deep space. The moment it enters other transparent mediums, like water or a thick piece of glass, it actually hits the brakes and slows down a bit. Section 2. The laws of reflection. The fundamental rules of bouncing light. And this whole concept brilliantly illustrates the two types of reflection we encounter every single day. First, we have specular reflection. This happens on incredibly smooth surfaces, giving you a crystal clear, perfect image, exactly like checking out your reflection in a perfectly still, glassy lake. But then we have diffuse reflection. If you drop a pebble into that exact same lake and the water starts rippling, the surface becomes rough. The light scatters everywhere, and suddenly your image becomes blurry, distorted, and unrecognizable. Now, when we get that perfect specular reflection, light is actually following two totally unbreakable rules. First, the incoming incident ray, the bouncing reflected ray, and the normal, which is just an imaginary perpendicular line, all lie in the exact same plane. Now, a huge misconception is thinking this means the floor. It doesn't. It actually means they all exist on the same vertical and visible frame. Second, the angle of incidence exactly equals the angle of reflection. That normal line acts as a perfect angle bisector, splitting the bounce right down the middle every single time. Section 3, the plane mirror truth. Let's talk about everyday reflections. Think about that flat mirror hanging in your bathroom. It actually has 5 unchangeable traits. Your reflection is at the exact same distance behind the mirror as you are in front of it. It's the same size, so no carnival funhouse shrinking or growing going on here. It's virtual, meaning the image is trapped inside the mirror. You couldn't, say, project it onto a movie screen. It's erect, meaning it's right side up. And finally, it's laterally inverted. Your left becomes the image's right. This is exactly why the word ambulance is written backward on emergency vans. So when you glance in your rearview mirror, lateral inversion flips it, and it reads perfectly forward. Section 4. Spherical mirrors unlocked. Time to dig into the math of curved optics. Now, there are 2 main types of curved mirrors. First is the concave mirror. A really great, simple trick to remember this one is to think of the opening of a cave. It bends inward and acts as a converging mirror, bringing all those light rays perfectly together. On the flip side, we have the convex mirror, which bulges outward and acts as a diverging mirror, scattering the light rays away from each other. To really understand how these work, we just need a quick map of their anatomy. Think of every curved mirror as just a sliced-off piece of a much larger, giant imaginary glass sphere. The pole, or P, is the exact midpoint of your specific mirror slice. The center of curvature, C, is the center of that giant imaginary sphere it was cut from. And the principal focus, F, is the magical halfway point between them, where parallel light perfectly converges. I know drawing ray diagrams can seem super intimidating at first, but it's incredibly simple because you only ever need 2 of these 4 rules to find an image. Rule 1, a ray coming in parallel bounces directly through the focus. Rule 2 is just the exact reverse. A ray passing through the focus bounces back parallel. Rule 3, a ray going through the center backtracks perfectly along its own original path. And Rule 4, a ray hitting the pole directly reflects at the exact same angle. Pick any 2 of those rays, trace them, see exactly where they cross, and boom, there's your image. So the crucial point is really looking at what happens with a concave mirror based on where you stand. Think about the first 5 scenarios here. Whether you're miles away or right up at the focus, the image is always real and inverted, meaning it's completely upside down. But look at case number 6. If you get really close, right between the focus and the pole, it becomes our VIP case. Suddenly the image flips to become virtual, erect, and massively enlarged. Now, while concave mirrors have all those different cases, convex mirrors are beautifully, refreshingly simple. I want you to enthusiastically burn this massive takeaway right into your brain. For convex mirrors, no matter where you place an object, the image will always be VED, virtual, erect, and diminished. It will always be trapped in the mirror, right side up and shrunken down. Always VED. And hey, to solve numerical problems, you just need the Cartesian sign convention. Let's demystify this math right here, right now. Just treat the mirror's pole exactly like the 0, 0 origin on a standard graph from your algebra class. Anything measured to the right or pointing up is positive. Anything measured to the left or pointing down is negative. If you stick to this simple grid, you will literally never fail a numerical optics problem. It's basically a cheat code. Section 5, Real-World Mirror Applications. Let's connect all this physics to the real world. Remember that awesome 6th VIP case for concave mirrors we talked about? Dentists and makeup artists exploit this specific physics trick every single day. By placing a tiny tooth, or your face, super close to the mirror, right between the pole and the focus, they get a magnified, beautifully clear, and upright virtual view. It takes something incredibly small and blows it up so they can see all the details perfectly. On the flip side, we have convex mirrors, which are heavily used for blind street corners and car rearview mirrors. This connects right back to our VED rule, because convex mirrors always make things virtual, erect, and diminished. It physically shrinks the reflection of cars and buildings down. This allows security guards and drivers to cram a massive, super wide field of view into one tiny, incredibly safe mirror. Honestly, it's just amazing how these strict, unbreakable laws of physics govern exactly what we see every moment of our lives. So I want to leave you with a quick, fun challenge. Right after this explainer, go grab a shiny, brand new spoon from your kitchen drawer. Look at the inside hollow part. That is your concave mirror, and you'll see your face completely upside down. Then flip it over to the bulging outside, your convex mirror, and you'll see a tiny, upright version of yourself. You can literally hold the profound physics of light right there in your own hands. Keep exploring, keep learning, and I will catch you in the next explainer.